course of
Fundamental of Electronics and Electrical Engineering.
this video lecture, I am going to discuss Unit 1, that is DC circuit. In the first video lecture, I have discussed topics like EMF, current, voltage, potential difference. So let us see what I am going to discuss in this video lecture. The first thing I am going to discuss is resistor, then inductor and capacitor. So let us start with the resistor. So to understand the resistor, here you can see one conductor is there which consists of electron and stationary atoms. Now, when potential difference is applied across the conductor, electron will start to move from negative terminal of the battery to the positive terminal of the battery. But while traveling, these free electrons will collide with the stationary atoms. And because of the collision, the flow of electron is reduced or restricted. So there is something which opposes the flow of electron. And the opposition offered by a substance to the flow of electric current is called its resistance. Because flow of electron is nothing but the flow of current. It is measured in terms of ohm, which is denoted by omega. Resistance can be also specified in kilo ohm, mega ohm. These are the different range in which it is specified. Now, let us see the factor affecting the value of the resistance. So first one, the resistance of a conductor is directly proportional to its length. So R is proportional to L. It is inversely proportional to its cross-sectional area. So R is proportional to 1 divided by A. It also depends on the types of material, nature of the material, and it also depends on the temperature. So these are the four parameters, factors on which resistance of a conductor depends. And we will discuss each and every factor in detail. So R is proportional to L divided by A. If we remove the proportionality sign, R is equal to rho L by A. Here, rho is a Greek letter, it is a constant, it is known as the resistivity or specific resistance of the material. Now, let us see each and every factor. The first one is the length of the conductor. R is proportional to L. So, if the length of the conductor is increased, then distance that free electron travel will also increase, and as a result, free electrons will be restricted by more atoms and molecules which are present in the long conductor, and obstruction collision is increased, then flow of electron is reduced, and flow of electron is reduced, so we can say current is reduced and resistance is increased. So as length of the conductor increases, resistance also increases. So here you can see there are two conductors, conductor A and conductor B. The length of the conductor A is L, length of the conductor B is 2L. Both are having same cross-sectional area, that is A meters square, and both are made of same material. So resistance offered by conductor B will be double than the resistance offered by conductor A in this particular case. The next one, it depends on its cross-sectional area. Resistance is inversely proportional to the cross-sectional area. Why? So if area of the cross-section of the conductor increase, the path for the flow of electron or current is also increased, and as the path increase, opposition offered is also decreased, and because of that, resistance is decreased. So resistance is inversely proportional to the cross-sectional area. Here again there are two conductors, conductor A and B, both are made up of same material. Length of both conductors are same, that is L meter. But cross-sectional area of conductor A is A meter square. Cross-sectional area of conductor B is E by 2 meter square. So here, resistance offered by conductor A will be half than the resistance offered by conductor B. The next one, the types of material. Different materials have different atomic structure because each material has different atomic weight and atomic number. And because of this, resistance offered by each material will be different. And because of what? Because of different number of free electrons available. Because every material has different free electrons available within them. Every atom has. So here there are two materials. One is two conductors are there. One is copper and another is aluminum. Both are having same length. Both are having same cross section area, but the atomic structure of both the materials are different, and both materials have different number of free electrons. So resistance offered by these two materials will be also different. The next one is the temperature. So what is happening if temperature is increased? If the temperature is increased of a substance, then molecules will vibrate more rapidly, and which will impede the movement of the free electrons through the substance. So here you can say as the temperature increases, molecules will start to vibrate and which will impede the flow of electron, and on increasing the temperature there is no further increase in free electrons. So ultimately as the temperature increases, flow of electron is reduced, resistance is also increased. So these are the four factors on which resistance of a resistor depends, of a conductor depends. Next one is the specific resistance or resistivity. So we have already proved that R is equal to rho L divided by A, where rho is a resistivity. Now in this equation, if we take L is equal to 1 meter and cross-sectional area is equal to 1 meter square, then R is equal to rho. So what will happen? So how we can define this specific resistance? So here you can see one conductor which is having 1 meter length and 1 meter square cross-sectional area. So specific resistance of a material is a resistance offered by 1 meter length of a wire of a material having an area of cross-section of 1 meter square. So basically, specific resistance of a material is a resistance offered by a conductor having 1 meter length and 1 meter square cross-sectional area. Unit of resistivity is ohm into meter. Another thing is a conductance. The reciprocal of resistance of a conductor is known as conductance, which is denoted by capital G. Resistance is denoted by capital R. So relationship between resistance and conductance is G is equal to 1 divided by R. Now we know resistance of a conductor is opposition to the current flow. The conductance of a conductor is an inducement to the current. Next one is an inductor. Basically it is an energy storing element. It is an element that stores electric energy in the form of magnetic field. It is also known as a coil. Inductance L is a property of inductor. Resistor is an element, resistance is property. Inductor is an element, inductance it is its property. So inductance is a property of coil to oppose any change in the magnitude or direction of the current flowing through it. When a varying current is applied to a coil or inductor, varying flux will be produced, and as a varying flux is produced, EMF gets induced in the coil. The unit of the inductor is Henry. It is also specified in terms of millihenry. Inductance of a coil is given by L is equal to N into phi divided by I, where N is the number of turns of the coil, phi is the flux linking with the coil, and I is the current flowing through the coil. So, inductance opposes any change in the magnitude or direction of the current flowing through it. Now, there are two types of inductor, fixed type inductor and variable type inductor. And these are the two symbols of fixed type inductor and variable type inductors. In the variable type inductor, the value of the inductance can be changed. The next one is a voltage current equation. As the current starts to flow through the coil, EMF gets induced in the coil. So voltage current relationship of a coil of an inductor is given by V is equal to L di by dt, where V is the voltage across the inductor and I is the current flowing through the inductor. Making di as a subject, di is equal to 1 divided by L V dt. Integrating both these sides, we can get I is equal to integration 1 divided by L. Next one is the power absorbed by inductor. So power is given by product of voltage and current. Now we have already proved Prove that V is equal to L di by dt and I is 1 over L integration V dt. So power can be also written as P is equal to L di by dt. Next one is the energy stored by inductor, because inductor is a basically energy storing element. So we can write E is equal to integration P dt, where P is a power. So we can write E is equal to integration L I di by dt into dt. So E is equal to L integration I di, and integration of I with respect to di is nothing but the I square by 2. So we can write energy E is equal to 1 by 2 Li square joule. So this is the energy stored by inductor. Now, inductors can be connected in series and parallel. If inductors are connected in series, then equivalent inductance is given by L1 plus L2, where L1 and L2 are the individual inductance of the coil. If inductors are connected in parallel, then equivalent inductance is given by L equivalent is equal to L1 L2 divided by L1 plus L2. Next element is a capacitor. It is an element which stores energy but in the form of fleeting charge. And capacitance is a property of a capacitor which stores the electric charge. It is measured in terms of farad. Now, farad is a big unit. So, capacitor is specified in terms of microfarad, picofarad, and nanofarad. The value of the capacitance is directly proportional to the area of the plate. It is inversely proportional to the distance between the two plates. It also depends on the absolute permittivity of a medium between the two plates. So we can write capacitance C is equal to epsilon 0 epsilon R A divided by D, where A is the area of the plate and D is the distance between the two plates. So this is the construction of capacitor. You can see it consists of two conducting plates which is separated by dielectric medium. And dielectric medium can be anything. And based on the dielectric medium, capacitors are classified into the air type capacitor, electrolyte capacitor, mica capacitor, paper capacitor, where air, mica all are nothing but the dielectric mediums. Now, voltage current equation in the case of capacitor. The current voltage relationship is given by C is equal to Q by V, where Q is a charge and V is a voltage. So we can write I is equal to dq by dt. Putting the value of Q, we can write I is equal to d by dt into Cv. So we can write I is equal to C dV by dt. So making dV as a subject, we can write dV is equal to 1 by C I dt, where V is a voltage across the capacitor and I is a current flowing through the capacitor. Now taking integration both the sides, integration dV is nothing but the V is equal to 1 over C integration I dt. Now power absorbed by the capacitor. So P is equal to V into I. So we can write VC dV by dt. Now energy stored by a capacitor. E is equal to integration P dt. So E is equal to integration V into C into dV by dt into dt. So E is equal to C integration V dV. Integration of V with respect to dV is nothing but the V square by 2. So energy E is equal to 1 divided by 2 Cv square joule. Capacitor can be connected in series or parallel. If capacitors are connected in series, then C equivalent is equal to C1 C2 divided by C1 plus C2. If capacitors are connected in parallel, then C equivalent is equal to C1 plus C2. So this is all about today's lecture. In this video lecture, I have discussed three elements: resistor, capacitor, and inductor. Hope you have enjoyed this video. See you soon in the next video of the DC circuit. Thank you for watching.